Atmospheric refraction. You must have observed that the apparent random wavering or flickering of an object seen through a turbulent stream of a hot air rising above a fire or a radiator, okay, which we have already seen. Okay, during the fire or a radiator, we are seeing that imaginary, okay, object. The air just above the fire become hotter than the air further up. The hotter air is lightened, less dense, and the cooler air above it and has a refractive index slightly less than that of a cooler. Okay, so if we compare a refractive index, then since the physical condition of a refracting medium air are not stationary, okay, which is not stationary, the apparent position of an object as seen through the hot air, which will be fluctuated. Okay, what we are saying that it gets fluctuated, and this wavering is thus an effect of a atmospheric refraction, and due to which atmospheric refraction can be seen. What is this? That refraction of a light by the earth atmosphere, due to which we will see a fluctuated object, okay, on a small scale in our local environment. The twinkling of a star is the similar phenomena on the much larger scale. Let us see how can it be explained. Okay, the twinkling of star. Okay, star which we are seeing that it get twinkled. Okay, that is also one of the phenomena of this only. Okay, due to which we will see a twinkling of star. Okay. Now the twinkling of a star. The twinkling of a star is due to the atmospheric refraction of a starlight. Okay, starlight which are coming from there, okay, from the atmosphere or from the sky. Okay, it get twinkled, and due to which a star get twinkling. Okay. The starlight on entering the earth atmosphere, when the starlight entered in the earth atmosphere, what will be seen? It will undergo refraction continuously before it reaches the earth. Okay, when a star reaches from the earth's atmosphere, at that time what we are saying that it get continuously refraction, continuously it get refracted, and due to its refraction, okay, before coming to the earth, we will see that some light or a starlight will be twinkled, and the atmospheric refraction occur in the medium of gradually changing refractive index. Okay, when it can be seen that twinkling of star, when both the refractive index of a two medium are changing. Okay, at that point atmospheric refraction can be seen, and since the atmosphere bends starlight towards the normal, okay, what? Okay, atmosphere will bend starlight towards the normal, it will bend towards a normal, and due to which apparent position of a star is slightly different from its actual position, and because of which, okay, we will see a star position slightly differ or far or displaced from the particular or actual position. Okay, and due to which apparent position, which we will see, that is known as apparent, and from the actual position, actually wherever it was there, okay, from there it get changed its direction. Okay, that we'll see here only. The star appears slightly higher above than its actual position when viewed near the horizon. Okay, here you can see, okay, that actual position of star is here, but then also we will see at a apparent star position only. Okay, so due to a refraction it will be seen. Further, this apparent position of a star is not stationary. Okay, that is not a stationary, but keep on changing slightly. Slightly it get changed from time to time. And since the physical condition of the Earth's atmosphere are not stationary, as was the case in the previous paragraph, since the stars are very distinct, they approximate point-size source of light. Okay, what will be seen that it will approximate a point-size source of light, and due to which a star position are distinct or can be seen distinct from its actual position, as the path of the ray of light coming from the star goes on varying slightly it get varied, and the apparent position of the star fluctuate, and the amount of starlight entering the eye will get fracture, and the stars sometimes appear brighter and at some time other time fainter, which is twinkling effect, okay, which we say it as a twinkling effect. How? Okay, once again I am repeating, when the light passes from the atmospheric refraction, at that time what will be seen? Okay, it get entered to our eyes, and due to which it get fracture. Okay, what will be seen? It get fracture, and due to which, okay, due to the atmospheric refraction, okay, sometimes star will be seen as a brighter, okay, its light will be brighter, but sometimes it get fainted, okay, due to which, okay, we say it as a twinkling or effect, and this effect is said to be twinkling effect. Okay, sometimes it look like a brighter, why the light sometimes look like a phantom, and due to which a twinkling effect can be seen, and this phenomenon is known as twinkling effect. Why don't the planet twinkle? The planets are much closer to the earth. Planets are much closer to the earth, then also it is not twinkling. Why? Are thus seen in the extended sources. If we consider a planet as a collection of a large number of point-side sources of light, the total variation in the amount of light entering our eyes from all the individual point-side sources will average out to zero, and therefore nullifying the twinkling effect. Okay, what will be seen? A planet, okay, which are very near to the earth, okay, all the planet will variate amount of light, okay, amount of light which are entering in our eyes, okay, every light or amount of light will nullify its own sources. What will be seen? It will nullify its own sources, and due to which total refraction will be zero, and therefore twinkling effect will be nullified. Okay, so it will not be seen as a twinkling. Okay, so we can see that planet cannot be seen as a twinkling, while starlight will be seen. Now, advanced sunrise and delayed sunlight. Okay, what is the phenomena of the advanced sunlight and delayed sunlight? The sun is the visible The sun is the visible to us about 2 minutes before the actual sunrise. Okay, sun is seen before 2 minutes from the actual sunrise, and about 2 minutes after the actual sunset because of atmospheric refraction. Okay, because of atmospheric refraction, we will see 2 minutes before the actual sunrise. Okay, and same way before sunrise, after 2 minutes also. Okay, 2 minutes after also after the sunset. Okay, it can be observed. Okay, sun can be easily observed. Why? Because of the atmospheric refraction. By the actual sunrise, we mean that actual crossing of the horizon by the sun. So the actual apparent position of the sun with respect to horizon. The time difference between the actual sunset and apparent sunset is about 2 minutes. Okay, the difference between actual and apparent sunset is 2 minutes. So that's why we can see after 2 minutes also sun can be seen easily. Okay, after sunset, okay, 2 minutes, up to 2 minutes we can observe a sun. The apparent fraction rate of a sun's disk at a sunrise and sunset is also due to the same phenomena. In same way, okay, sunrise and sunset, both the phenomena are seen because of this. Okay, why? Which phenomena? Okay, apparent and actual position. Okay, of both of them. Okay, with respect to horizon. Okay, are difference of which, okay, from actual to apparent there is a distance of 2 minutes. That's why we can see 2 minutes earlier and 2 minutes after sunset. Okay, we will observe sun rise before 2 minutes and after sunset 2 minutes. Okay, so here you can see that apparent position of sun and real position of a sun. Okay, because of a atmospheric refraction. Okay, Now the scattering of light. Okay, how the light is scattered. Okay, the interplay of a light with object around us give a rise to the several spectacular phenomena in nature. The blue color of sky, current of a water is deep sea. The reddening of a sun at rise and the sunset are some of the wonderful phenomena we are familiar with. Okay, we know it very well. The sky is blue in color. Same way, water for deep sea, that is also blue. Same way, redness, sun, which are reddening of a sun at sunrise and the sunset, are some of the wonderful phenomena which we are familiar with, okay, which we are observing every day. Okay, when it is rising, okay, the sun are reddish, okay, it look like a red. Same way, when it is set, okay, sun get set, at that time also we can see that sun is little bit red, okay, in color. The previous class we have learned about scattering of light by choroidal particle in 9th standard. Okay, we have already studied a scattering of light by the choroidal particle. The path of a beam of light passing through a true solution is not visible. Okay, beam of light, when it passes through the blue solution, it will not be observed. Okay, however, its path become visible through a choroidal solution, but its path can be visible by choroidal solution when the size of a particle are relatively large. Okay, whenever the size of a particle are large, at that time only we can observe it. Okay, so same phenomena will be seen. Tyndall effect, okay, which we have already studied in 9th also. Okay. The earth atmosphere is heterogeneous mixture of minute particles. Okay, in earth atmosphere we are observing a heterogeneous mixture of minute particles. Okay, minute particles are present in heterogeneous mixture form. This particle includes smoke, tiny water drop, suspended particle of dust, and molecule of air. Okay, all these are the particles, okay, which are observed in the atmosphere. When a beam of light strikes such fine particle, when a beam of light passing through this particle, what will be seen? The path of the beam become visible, and due to which we can see that a beam of light path can be visible, and this particle can be observed carefully. The light reaches us after being refracted diffusely by this particle, and this phenomenon is called scattering of choroidal particle, give rise to a Tyndall effect. Okay, once again I am repeating how this phenomenon is working. In atmosphere, okay, there is a presence of many particles like smoke, tiny water drop, suspended particle, dust, and molecule of air. Okay, when all these particles, okay, when a beam of light strike to all these particles, what will be seen? Fine particle like this. Okay, that beam of light become visible. Okay, path of the beam become visible, path of the beam become visible, and this particle can be seen easily, and the light reaches our eyes by refracted diffusely by this particle. Okay, what will be seen? Beam of light get refracted by this particle, and due to which, due to this phenomena, scattering of light gets scattered by the choroidal particle. Okay, choroidal particle which are present in our atmosphere, that will scatter the light, and due to which, okay, this phenomena of scattering of light by the choroidal particle, okay, is said to be a Tyndall effect. What we say it as a Tyndall effect? We are observing that a closed room, okay, closed room is there, one hole is there in that room. What will be seen? And when a beam of light, okay, is passed from that hole, okay, small particle can be observed of a dust particle. That particle is of dust particle, which can be observed easily, which we said is a Tyndall effect. Okay, which you have studied in class 9. Okay, which we have already studied in class 9. Okay, this phenomena is seen when a fine beam of sunlight enters a smoke filled room through a small hole. Okay, just now I have discussed. Okay, when a beam of light or a beam of sunlight enter to the smoke filled room through a small hole, okay, through a small hole, what will be seen? A scattering of light make the particle visible. due to the scattering of light, particle can be visible easily. And the Tyndall effect can also be observed. What will be observed? Tyndall effect can be observed by sunlight passing through the canopy of a dense forest. Okay, in the dense forest of a canopy, that also we can see. Here, tiny water droplet in the mist scatter light. Okay, tiny water droplet which are there, that will also scatter the light. The color of the scattering light depend on the size of the scattering particle. Okay, the color of the light is totally depends on the size of the scattering particle. Very fine particles scatter mainly blue light, while particle of the larger size scatter light of a longer wavelength. Okay, once again I am repeating. When a very fine particle scatter, okay, when a fine particle is scattering a beam of light, at that time it will give blue color. What it will give? It will give blue color, but if the scattering particle, okay, particle size of a scattering are larger, then what will be seen? It will give a longer wavelength color. If the size of the scattering particle is large enough, then scattered light may be even appear white. Okay, what will be seen? It can be observed white also if the size of the scattering particle are large enough. Okay, then why is the color of the clear sky blue? Okay, why the sky is blue in color? The molecule of the air and other fine particles in the atmosphere have a size smaller than the wavelength of visible light. Molecule of air and other fine particles which are present in an atmosphere, okay, have a size smaller. Okay, they are small in size, okay, than the wavelength of visible light. What? Okay, molecules which are present in a air as well as fine particles which are present in an atmosphere, okay, they have a size very small as compared to the wavelength of a visible light. Visible light compared with the particle of the molecule or a particle of a atmosphere, okay, which are very less as compared to visible light, and these are more effective in scattering of light, and due to which scattering of light of a shorter wavelength which is blue, okay, which we have already studied. Okay, so it will give a scattering of light of a shorter wavelength which is blue, and then light of a longer wavelength at a red end. The red light have wavelength about 1.8 times greater than blue. Okay, if we compare, okay, red colored light, okay, red light have a 1.8 times greater wavelength as compared to a blue. From this we can say that blue have a shorter wavelength while red have a larger wavelength as compared to this. Okay, and thus when a sunlight passing through the atmosphere, okay, when a sunlight passing through the atmosphere, okay, atmosphere in which fine particle is present as well as molecule of the air is present, okay, the fine particle in the air scatter blue color, and due to which it will scatter only blue color, okay, because we have already studied, okay, in this 11.6.2 that a molecule of the air and the other fine particle which are present in an atmosphere have a size very small, and because of its small size, okay, small size, what will be seen? A sunlight which are incident on that atmosphere, okay, containing this molecule, okay, will give a shorter wavelength light. Which light? Shorter wavelength light. Okay, so it is blue. Okay, and shorter wavelength means what? Okay, blue color light, which we say it as a shorter wavelength. Okay, so more stronger than red. The scattered light, blue light, enter our eyes. Now, what will be seen? Okay, from the sunlight. Sunlight is scattering. Okay, sunlight gets scattered by a tiny particle of an atmosphere which are present in atmosphere, that will what? Okay, that will give shorter wavelength light which is a blue. So that blue light, okay, which are scattered, that will enter in our eyes. Where? Okay, that will enter in our eyes, and due to which we will observe that the sky is blue in color. If the earth had no atmosphere, okay, here we have seen that atmosphere are there in the earth. But if the atmosphere are not there, okay, if we consider or imagine that if the earth have no atmosphere, then what will be seen? There will be no have been any scattering. No scattering will be seen. And then the sky would look dark. Then what will be seen? That the sky will look dark, and the sky appear dark to passenger flying at very high altitude, as scattering is not prominent at such height, and due to which sky will look dark. Okay, you might have observed that the danger signal light are red in color. Okay, why? Okay, because red is least scattered by the fog and smoke. Okay, so it can be observed from far distance also. Okay, therefore it can be seen from the same color at a distance. Okay, from far distance also red color can be seen, because why? Okay, red color will not scatter, okay, greater as compared to a blue, so it can be seen from far distance also. Now the color of the sun at sunrise and sunset. Have you seen the sky and the sun at a sunset and sunrise? Have you wondered as to why the sun and the surrounding sky appear red? Let us do any activity to understand the blue color of sky and reddish appearance of the sun at the sunrise and sunset. Okay, now we will do one activity through which we will consider that how it can be observed red and blue. You will find a fine microscope sulfur particle precipitate in about 2 to 3 minutes. Okay, 2 to 3 minutes what we have taken a sulfur particle. Okay, precipitate sulfur particle. As a sulfur particle began to form, you can observe that a blue light from the three side. Okay, from the three side you can see that blue light are inciding, okay, from the glass tank. This is due to the scattering of shorter wavelength by the minute colloidal sulfur particle. Here we have taken sulfur particle, and by this observe the color the transmitted light from the fourth side of the glass tank facing the circular hole. Okay, facing the circular, if we observe, then what will be seen? That it is interesting to observe at a first the orange red color. Okay, first we will observe a orange red color, then the bright crimson red color on the screen. On the screen we will observe crimson red color. Okay, so this way whole phenomena is seen, and this activity demonstrates that the scattering of light help by understand the bluish color of the sky and the reddish appearance of the sun at the sunrise and sunset. Okay, during the sunrise, okay, and sunset, okay, how the bluish color of the sky is seen and how the reddish appearance can be seen. Okay, so that can be observed. Now the light from the sun near the horizon passes through the thicker layer of air and larger distance from the earth atmosphere before reaching our eyes. Okay, as you can see in 11.12. Okay, what the sun nearer overhead, okay, less blue scatter. Okay, blue color will scatter less, but as the blue color is, okay, you can see that sun near the horizon, what will be seen? Blue scattered away, sun appear reddish. If the blue scattered, then what will be seen? That sun will appear reddish, but on a height or overhead, okay, blue color will scatter less, and due to which, okay, we can observe it very well. Okay, however, the light from the sun overhead will travel relatively shorter distance. Okay, it will travel shorter distance. At noon, the sun appears white as only a ritter of blue and violet color of scattered. Due to the blue and violet color scattering, okay, at noon sun is appeared white as only, okay, and near the horizon most of the blue light and the total wavelength are scattered away. What will be seen that at that time a blue color light are scattered away the particle, and therefore the light that reaches our eye are longer wavelength, due to which a light which is reaching in our eyes will have a longer wavelength as compared to previous one, and this give a rise to the reddish appearance of a sign, okay, which will give a reddish appearance of a sun.
We've observed some natural phenomena in our daily life, such as the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. The twinkling of stars is a similar phenomenon. This wavering is thus an effect of atmospheric refraction of light by the Earth's atmosphere in our local environment. Let us discuss about them. Twinkling of stars. The twinkling of a star is due to atmospheric refraction of starlight. The scientific name for the twinkling of stars is stellar scintillation or astronomical scintillation. Stars twinkle when we see them from the Earth's surface because we are viewing them through thick layers of turbulent, moving air in the Earth's atmosphere. Stars, except for the sun, appear as tiny dots in the sky. As their light travels through the many layers of the Earth's atmosphere, the light of the star is bent, refracted many times, and in random directions. Light is bent when it hits a change in density, like a pocket of cold air or hot air. This random refraction results in the star winking out. It looks as though the star moves a bit, and our eye interprets this as twinkling. Stars closer to the horizon appear to twinkle more than stars that are overhead. This is because the light of stars near the horizon has to travel through more air than the light of stars overhead, and so is subject to more refraction. Also, planets do not usually twinkle because they are so close to us. They appear big enough that the twinkling is not noticeable, except when the air is extremely turbulent. Stars would not appear to twinkle if we viewed them from outer space or from a planet or moon that didn't have an atmosphere. Apparent position of sun. Because of atmospheric refraction, we do not see the sun or the stars in its true position except when it is directly overhead. As a ray of light from the sun enters Earth's atmospheric at B, it continuously bends towards the radius of the Earth. The ray of light will reach the observer at O, as if it had come in the direction AO instead of in its true direction BO. Consequently, we do not see the true position of the sun. It is due to atmospheric refraction that the sun is visible before actual sunrise and after actual sunset. Do you know this fact? The sun appears to rise 2 minutes before the actual rise, and it continues to be seen 2 minutes after it has actually set.